Right, in this particular video, let's look at an example of exponential growth. One of the most familiar is an investment earning continuously compounded interest. So suppose a principal is invested at an annual interest rate R compounded once a year. If the new interest is added to the principal at the end of the year, then we get a new balance. This pattern of multiplying the previous example by 1 plus r is then repeated each successive year. Let's take a look at it. Time in years, 0, the principal equals the principal. But at the end of the first year, notice the principal is 1 plus r. Now, at the end of the second year, we're going to take P1 and multiply it by 1 plus r. But if we make appropriate substitutions, that's P times 1 plus r times 1 plus r, which is P times 1 plus r squared. 2 years, we square it. Do you see a pattern? Let's go down here. How about n years? Or t years, sorry, I called it t years. The principal then, or what the amount we have invested, will be P times 1 plus r to the t power. So let's do an example. Let's let the principal be $1,000. The interest rate 6%. Oh, don't you wish you could get 6%? And the time 10 years. So we're going to say 1,000 times 1 plus 0.06, all raised to the 10th power. Now we are not going to do that by hand. So now we get out our good old calculators again. And we use the calculator there, being very careful to type everything in correctly. And so, in this case, we're going to have, at the end of 10 years, an extra $790. Now, sometimes we compound more frequently. For example, semi-annually is 2 times a year, quarterly, 4 times a year, monthly, 12 times a year, daily, 365 times per year. The product NT represents the total number of times the interest will be compounded. If compounding more than once a year, though, the interest rate must be adjusted accordingly. You're not going to get R% every quarter, so we get R over N every quarter, but it's still a significant increase. So again, let's let a principal of $1,500, 5% rate. Notice we got to divide it by 4. We're going to get 1.25% every quarter, but it's going to earn interest. So go to the calculator and let's see how much interest we actually are getting here. Right, we got to type it in very carefully. Notice the 0.05 divided by 4. Now watch when I raise it. Parentheses 5 times 4. If you don't put those parentheses, it'll raise it to the 5th power and then multiply the whole thing by 4, and you will not have the correct answer. So here, we're going to gain a little over $400. Let's do another example. Let's suppose in this case that the principal is $2,000. Our interest rate is 4%. And let's go for 12 years. Let's do it monthly, all right? In other words, n equals 12. So our formula is going to be a equals 2,000 times 1 plus 0.04 over 12 to the 12 times 12 power. Notice we don't get much interest each month, but it accumulates. So we're going to go in here and we're going to do the arithmetic using technology, because this one would be terrible. Think that we'd have to raise that to the 144th power, because that's what 12 times 12. Can you imagine before calculators when you had to take something like that and raise it to the 144th power? Whoa, no way. So we go back here and we see that, look, monthly we gained over $1,000 in 12 years. So when the corresponding number of compoundings increases without bound, this process takes on a little different approach called continuous compounding. Now in calculus, you're going to see how as m increases without bounds, that 1 plus 1 over m to the m goes to e. So we stick that in. We raise it to the RT power, and look what we get. P times e to the RT. I bet you've seen that somewhere. This result is part of the reason that e is the natural choice for a base of an exponential function. We'll use this a lot, both in this course and in calculus. So let's compute the accumulated amount of P equal 5,000, R is 4%, 6 years when compounded annually. Then let's compound it quarterly. And we're going to do all this on the calculator when we get done. So let's go for quarterly here. And we're going to see how things grow. Monthly, always got to stick in monthly because the algebra on that, or the arithmetic rather, would be so ghastly. And continuously. Right now, continuously is another one I don't want to try to do by hand. Notice how the formula changes. You don't have any 1 plus something over 12. It's e to the 0.04 over 6. So we have 5,000 times, and we're going to start with the annual 1 plus 0.04 raised to the 6 times 6, or annually we make $6,326.60. Now, let's see if we make more by doing it quarterly. We better, because we got interest every quarter, and that earned interest. All right, so let's see what we get here. Aha! This time we get $6,348. Notice we gained about $22. Not bad. Let's see how much we gain by letting it go monthly over doing it quarterly. We may gain quite a bit here. Let's see. I doubt it though. Oh, about $5 more. Now let's see if continuously makes any kind of a big change. Don't be surprised if you don't see a big change when you do it continuously. Let's give it time here to do the computations for us. No, see, you only gain a little over, not even $3. Continuously is okay on huge amounts, but it's not good on $5,000. So we'll go back here and we'll stick our numbers in that we have computed with our calculators. It'll take a minute for me to write all of those in there, but you remember what they are because you had your calculator sitting there so that you could remember them. Now, there are formulas for compound interest going to come up here in a minute, and class, you have got to memorize them. I'm going to put a great big red circle around them. For n compoundings per year, you've got to know that formula. Continuous compounding, you've got to know that formula. You will need it on quizzes and tests.